Welcome to the lecture on high temperature corrosion of metals and alloys. So in this lecture, first I will give you a context. Why do we need high temperature materials and why do we care about high temperature corrosion? That gives you a practical understanding of what happens to the material and how it interacts with the material at high temperatures. By high temperatures, we mean it's more than 0.5 times the melting point of the given material. Then after establishing this context, we will talk about the fundamentals, the thermodynamics and kinetics of high temperature corrosion. Then we will end this lecture with a practical example based on current research that we are doing. It's also connected to the industry where we are trying to make additively manufactured turbine center frame using a nickel-based superalloy 247. So we will see how we can study the oxidation. It also involves some modeling techniques, how we use experiments together with modeling to understand material behavior.
Coming to the outline of this lecture, first we will talk about the need for high temperature alloys along with practical applications for high temperature alloys, and then we will talk about general property requirements for high temperature alloys and how we as engineers and scientists are trying to push the limits of performance by going to higher and higher temperatures. And then we will talk about the protection against high temperature environmental degradation. What are all the methods that we use as engineers and scientists to mitigate the degradation process? And then, because the extrinsic method of coating a material is outside the scope of the topic of this class, and it is covered in later class called as surface modification techniques, we will focus mainly on the intrinsic methods, how by alloying we can tune oxide scale formation and get desired properties. In that we will also talk about thermodynamics, the Ellingham diagram and other diagrams in thermodynamics for real life alloys, and we will talk about oxide scale formation and growth and some growth laws, and there will be all along there will be an emphasis on the real life examples, including some of the work that we have been currently doing for General Electric company. So, and then we will briefly talk about the Wagner's criteria for internal versus external oxidation, how we like to have an external scale to form rather than forming a internal oxide precipitate which might degrade the mechanical integrity of the components. And we'll also talk about some alloy development strategies, some of the challenges and opportunities that lie in this field, and how you can contribute to this field as a corrosion engineer. So that would be the overall outline of the lecture. So let's jump into the content of the lecture by starting with the need for high temperature alloys.
Coming to the need for high temperature alloys. So what is first high temperature in this context? In this context, as I already mentioned in the first, when I was explaining the first two slides, I was saying it should be above 0.5 times the melting point of material. But in general, in industrial context, we usually use uh, the word high temperature application for temperatures which exceed 500 degrees Celsius, and we have operating temperatures up to 1200 degrees Celsius. In this case, we only use materials that has high melting point. Not as high melting point like a refractory material. We can also use some refractory materials for some of the high temperature applications. But most commonly used industrial materials are either iron based materials or nickel based materials or cobalt based alloys. So in the context of this lecture, we will define anything more than 500 degrees Celsius as a high temperature environment and height. We will talk whatever material degradation that occurs due to the interaction with the environment at this temperature as high temperature corrosion. Where do we encounter these high temperature conditions? One very common example that everybody is familiar with is, at least uh, many of you would have traveled in airplanes. So airplanes usually use something called as a jet engine, and in this, uh, the at the hottest part of this engine, we can even get to temperatures as hot as 1200 degrees Celsius. And there is an important industrial process of steam cracking, which is used to produce this hydrocarbon. For example, this ethylene pyrolysis. These are held in these big tubes that are there in the picture in the middle. So these can operate at temperatures like 700, 800 degrees Celsius. And these, if you see, the pipes look smaller, but these are very heavy, and the self weight due to the acting upon the gravity itself can cause high temperature deformation in the form of creep. And in addition to the aggressive environment of steam on one hand and the hydrocarbon on the other hand, it can both corrode this material at this operating conditions. And coming to power generation, so starting from conventional fossil fuel based thermal power generation to modern day clean energy technologies such as concentrated solar power. For example, this concentrated solar power, what it does is the concentrate, these are these mirrors, which are called as heliostats. So when sunlight falls on it and it gets reflected, and it gets converged into this tower called as the receiver tower, then the heat energy is collected, and then it is used to vaporize water, and the steam goes and turns this turbine, and we get electricity out of it. In this technology also, this turbine, which is interacting with the steam, so the turbine materials should be resistant to high temperature corrosion. So we have numerous applications. These are just some examples of applications. So if you search for high temperature alloys and high temperature applications in the internet, you will get numerous more examples. But these three examples are something to give you an idea, basic idea, why do we need high temperature alloys, and give a definition of high temperature alloy in the context of this course. I gave some applications where high temperature was encountered. But why do we need to even operate at high temperatures? That's a simple question. Why can't we operate certain things at room temperature? The answer to that is quite clear. If we look at the operation of a jet engine, the gas turbine engine, what happens is that we get fresh air from the atmosphere, and it gets fed into through these fans. You can see huge fans if you are sitting in a window seat in an aircraft. You can, if you can look outside, if you're sitting near the engine, you can see big fans rotating in the front side of the engine. These fans are just sucking the air that is coming in front of it as the aircraft is trying to run. So this air gets sucked into this engine, and then it goes through something called as a compressor. So in this compressor, if you took a look at this diagram, okay, all these things are taken from Wikipedia. So this is called as a Brayton cycle or Joule cycle. In this cycle, so we have an isentropic compression. So you heat it. So as you compress, the temperature increases. You can see you go from T1 to T2, and then in the second stage, we allow it to, we inject the fuel, and then it is allowed to combust. So that acts as a heat input. So there is no temperature change here because it's already hot and it burns the fuel, and then it expands into the turbine. So this is an isentropic expansion into the turbine, and then when the exhaust gases get out, you get back to the initial temperature that's outside here. So it is the cycle. So the Q out is in the form of heat that is emitted in the exhaust gas, and we also get work out of it as the compressed air that burns with the fuel, and then it expands in the turbine and it turns the turbine. That gets the work out of it, and then that does the work to keep the aircraft being continued to be propelled. If you consider the efficiency of this entire cycle, this thermodynamic cycle, you get the efficiency will get close to 1 if this becomes less than, it becomes a small value. If this fraction T1 by T2 becomes a very small value, you will get efficiency 1. So whatever energy that you input it, you will get 100% conversion of this thermal energy into mechanical work. But we cannot change the T1 because it is the air that is in the outside atmosphere. It's already pretty cold. If you saw the computer screen while you are in an aircraft, it would say the outside temperature is some minus 30, minus 35 degrees Celsius. It's already low, and it's we cannot manipulate it. It is controlled by uh, the environment in which it is operating. But T2, it is the operating temperature of the turbine. So if I can increase this T2, or the temperature that is resultant from the compression to the stage 2, if I can go to higher temperatures, then my efficiency increases. That's why we need high temperatures. So that explains the need for high temperature. This is just an example using this Joule or Brayton cycle, but it's even if you use a Carnot cycle, it would still be the T2 should be very high. So the T2 is the temperature after compression in this particular cycle. So in this slide, we show the current state of high temperature materials. This is in the context of, again, gas turbine engine, because it's a most widely used application both in power generation and as well as transportation. So here, the operating temperature is decided based on, okay, the most aggressive form of failure. In this case, creep life is one such metric that can tell about the failure life. So this is for 1,000-hour creep life at 137 megapascal. So this temperature axis is in degrees Celsius, and this is the year in which the material was developed. So in the beginning, we were using some wrought alloys, most are nickel-based alloys, and then we have conventionally cast alloy that came in the second generation. And then in between, we had directionally solidified. And now the current state of the art is we use single crystalline material that can provide adequate creep life even at operating temperatures such as 1050. We don't know whether it is going to continue in this direction. It is going to incrementally, we are going to increase the operating temperature, or we are going to suddenly go to a new technology that would sudden jump in operating temperature can be achieved. There are numerous research into some refractory high entropy alloys and some titanium and iron based superalloys, not iron based, sorry. Iron based superalloys are mainly for slightly lower temperature applications. If you think about chromium based superalloys or titanium based superalloys, they are trying to achieve much higher temperatures. So if they succeed, there will be a sudden jump in the current state from here to here somewhere. Or there are two routes, whether we are going to jump to, there's going to be a sudden technological jump, or it's going to incrementally go like this over every year. So if we jump here, then it's great. So we don't need to worry about nickel-based superalloys anymore, because we can operate things at much higher temperatures with a new material. Maybe it is a ceramic material or a refractory material, but we don't know. But in current state, it looks like we are taking this trajectory that we are incrementally improving the material properties here. But will it saturate at some point? We don't know. So This is the current state of the material technology in the context of high temperature materials. So the way we went from wrought to conventionally cast to single crystalline material is mainly driven by the dependence of creep resistance on the grain size. So if you have grain boundaries, then they start to slide at high temperatures, so which can reduce the mechanical properties. Uh, in case if you have a single crystal, all grain boundaries are eliminated, so you can improve the creep life, and consequently, if you improve one part of one property without affecting too much of other properties, you will get lifetime enhancement. So that's why we have from wrought to conventionally cast to single crystal alloys. In this slide, we are showing what are the special property requirements for high temperature alloys. These are excluding some of the common needs for general structural application. And I am also not talking about an obvious variable, that is the cost is a huge variable, and huge determining factor is the cost of the material. So that usually determines whether I can use this material or not. But in terms of material property requirements, what are all the properties that are needed? As I mentioned earlier, we need to have resistance to creep, because creep is a huge problem at high temperature, because creep happens at constant load, and creep can happen much below the yield point. So you are not expecting the material to deform under normal condition, but if you apply stress that is less than yield strength, even sometimes even 10% of yield strength is sufficient for creep to occur. If you apply this constant stress, what happens over time is that the materials start to deform. So this usually is a problem above 0.5 times the melting point of the material. So we need to care about creep resistance whenever we talk about high temperature alloys. Another thing that is discussed in the context of this particular course is the resistance to reactive environments. Usually the reactive environments comprises of oxygen is the main culprit, because in the first lecture I told we extract mainly from the oxide ore, so metal wants to become oxide, and at high temperatures and you have gaseous oxygen, so the thermodynamic driving force for oxidation of any metal is actually very high, and particularly of some metals. And we also have, in some applications, we can have carbon dioxide that can affect the material. We can also have steam that can create problem, H2O. We can also have other gases like this H2S, the hydrogen sulfide, can have an impact. So all these are reactive environments. That's why I used the word reactive, because it reacts with the material and degrades the properties. And another thing that we need is microstructural stability, because properties are controlled by microstructure. And if my microstructure evolves during the service, it is a problem for my application. For example, you want to select a material. If you have a precipitation hardened material, let's say there's a phase diagram here. So this is temperature and this is the alloy composition. You have a two-phase region B, let's say it's a alloying element B. You have an alpha plus beta phase region here. This is the phase diagram. So you want to choose the material below the solvus temperature, because this precipitation, you might use this precipitate for hardening, but if your operating temperature is here, then even if you started with two-phase material that had all the strength, you would, as soon as you go to this temperature, you will dissolve the precipitate and you lose the property. So you should choose the material such that the solvus temperature is above the intended operating temperature. So the microstructural stability is very important for high temperature environment, because microstructure can evolve quite strongly, because the diffusion is very fast at high temperatures. So we need to be careful and consider high temperature microstructural stability. And there is a link between these two. As we will see, that the surface reaction to the reactive environment in the form of either oxygen or steam, it can consume certain alloying elements, and it can, in turn, it can affect the microstructural stability, because if certain alloying elements is decreased, so you chose a material that was here. The operating temperature was here, so you are in the two-phase region, you have enough precipitate, you feel happy. But if oxidation or any this carbonization consumes this element B to form either oxide or carbide, then locally your composition of B decreases, and you might cross the solvus line at some point, and you will have a precipitate dissolution zone beneath this oxide or carbide layer that formed in the material. So that can have local microstructural instability, and that can also degrade your property. So the microstructure affects the resistance to the properties, because certain microstructural features such as grain boundaries can be involved in the oxidation. So there is this way coupling. The other way coupling is that the reactive environments can create and lead to local microstructural instabilities. So far, I have talked mainly generally about high temperature alloys, high temperature materials. But now jumping into the real topic of this lecture, that is the high temperature corrosion or resistance to reactive degradation of material in high temperature environments. So we need to have a slow kinetics of corrosive attack. What I mean by this is that my metal or alloy should not be consumed. The consumption rate of metal consumption or the alloy consumption rate should be very, very minimal. So, and then there should not be any localized internal attack. If oxygen penetrates into the material and it can oxidize within the material, for example, if we oxidize the grain boundaries of the material, then it is bad, because oxides are brittle while the metal is ductile. So this brittle link across these grain boundaries in the form of intergranular oxidation. This is not intergranular corrosion, it is intergranular oxidation. In intergranular corrosion, you consume metals selectively from the grain boundaries, but in intergranular oxidation, you form oxides along the grain boundaries. These are like oxide precipitates, continuous oxide precipitates along the grain boundaries. This can really cripple the mechanical properties. And then this corrosion should not form any liquid or volatile corrosion product. So what we want to form is something like this. I want to have a material, this is the material, let's say, and if we change the color, let's say this is an oxide scale that forms, or probably it's a wrong color, maybe we can use this color. So this is your substrate. This is the component that you use in service. And this develops an oxide film or a scale, because in this context we should really call it scale, because these are thick. These are not nanometric scale films that we talked in passivity. These are sometimes some microns, some 5-10 microns thick. So if this forms a protective scale, a solid scale that prevents further penetration of oxygen, then I am safe. Instead of forming this kind of layer, if my material start to just produce some gas, releases some gaseous corrosion product or meltable corrosion product or molten corrosion product, it's a danger. So I don't want that to happen. So these are the main three conditions that I need to care about. And this is achieved mainly by the protective scale formation. And this is also achieved by the protective scale formation. And we can, if we form a compact solid scale, we can also prevent this. So if all these three things are prevented, which is usually achieved by this protective oxide scale, then we are safe in terms of high temperature corrosion properties. So this slide gives you a brief overview of approaches we take to mitigate high temperature oxidation. One is an intrinsic method that we change the material. Like we change there is a concept of alloy design. We change the alloy composition, like play around with certain beneficial alloying elements, such as aluminum or chromium. We will see why aluminum and chromium are beneficial in the upcoming slides when we are talking about the fundamentals of this high temperature corrosion process. To alter these alloying elements or reduce certain alloying elements that are deleterious for the properties, such as reduce the tungsten content. The tungsten can form volatile oxide, or molybdenum content that can form volatile gaseous corrosion product in high temperature. So we need to be careful with molybdenum and tungsten at high temperatures, because in aqueous corrosion, so far, whatever we have discussed, we have always discussed tungsten and molybdenum as beneficial alloying elements. But in the high temperature oxidation, we do not consider these things as beneficial alloying elements. So we need to be very careful not to think tungsten and molybdenum as beneficial alloying elements in the context of high temperature oxidation. It's very common mistake for students to do and consider tungsten and molybdenum to be uh, beneficial for high temperature oxidation resistance. And we can also tune the microstructure. Like for example, if we need a fine grain size, so fine grain size bring in certain advantages, while coarse grains bring in certain other advantages. So we need to think carefully about what we want to prevent, what is the main issue for this alloy. So engineer the microstructure by designing heat treatments, and so on and so forth. Another method is an extrinsic method. So this is not changing the material, so the change is from outside the material. You apply a coating. Thermal barrier coatings are usually applied, though those can provide resistance to high temperature degradation. So we will cover more about this topic in another course that is called as the surface modification techniques. Some of you might have already taken this course. Some of you will take this course in the next summer semester. So there we will talk more details about the thermal barrier coating. But at this point, we will leave this matter. In this lecture. We will not come back to this topic again. We will mainly focus on this topic, which is the intrinsic method, in the rest of this lecture. So now I have told you the approaches to protect against high temperature oxidation, but we need to understand fundamentals. So far I have been giving examples from practical applications, how they are used and why do we need all these things. But in order to uh, for you to succeed as an engineer in field, you need to understand the fundamentals. If you do not understand the fundamentals, you are not going to solve any practical problem. So the theory is very important. If you want to solve and develop, if you want to be an innovator and solve problems, you need to understand the theory first. Without theoretical understanding, you will not be able to solve any practical problem. So even though theory might be boring, it is important to understand the fundamental elementary processes and mechanisms to succeed as an engineer or a scientist. So that must be made very clear at this point for all the students that are listening to this lecture.
Now we are getting started into the fundamentals of high temperature oxidation. First concept that you need to always understand is these metals and alloys are inherently unstable in these high temperature service environments. Because if you see the free energy of formation of oxides, they are all negative, which means that the metal to metal oxide transformation is spontaneous. So what does that mean? So there are two options for the metal. If you expose it to a high temperature atmosphere, it can either become a single piece of monolith of oxide, so entire metal gets converted into oxide. This is not what we want. So let's say MXOY, because the stoichiometry can be anything, it needs not be MO. Or we can form, you can retain most of the metal, but you form a thin layer or a protective layer of this oxide. So we prefer this protective scale formation. We prefer this, we don't prefer this. So to get to this situation, what is needed? First, we need to form very stable oxide. So if you have unstable oxides, then it is difficult to form the oxide itself. For example, the case of nickel, the free energy is rather uh, less negative, which means that nickel oxides are less stable. But on the other hand, if you see oxides such as aluminum or silicon or chromium, they form very stable oxides. But is the stability enough? Because if an oxide is stable, we can still get to this case 1, but we don't want case 1. For example, if you have magnesium or calcium, they actually form more stable oxide when compared to aluminum or chromium, but they are not protective scale formers because they lead to this case 1 when the entire metal quickly converts into just a piece of oxide. So that's why even though magnesium and calcium forms more stable oxides, they cannot form protective scales. So that brings to our next point, that thermodynamic stability is not sufficient to form protective scale. The thermodynamic stability of oxide is important, but at the same time it should grow slowly such that the entire metal is not consumed in the process, which means kinetics is important. So I want to spend some more time on the Ellingham diagram discussing about the 3 auxiliary axes that are present in the diagram apart from the temperature and the free energy axis. So what are those axes? You can see on the rightmost corner we have an axis. Let me mark this axis. This is PO2 axis, which is oxygen partial pressure axis. So I can draw this, and there is an L-shaped thing that is running here. So what we have is this is the outermost L, and then we have another L-shaped, another inverted C-shaped axis, which is this hydrogen to water vapor ratio. That is the second axis, auxiliary axis, and the third auxiliary axis is the monoxide carbon dioxide ratio. So this is another axis that's also continuing downstairs, and there is an L-shaped component here. So let me erase all these lines. So these are the 3 auxiliary axes that I am talking about. So how are they relevant? So the oxygen partial pressure is relevant because in gaseous state mixture, partial pressure is something that signifies or that can be used as a proxy for activity of a specific species. In this case, if you have oxidation taking place in air, we have 78% N2 and we have 21% oxygen by volume, 78% and oxygen 21%. In terms of oxygen partial pressure, in our normal atmosphere which we breathe has around oxygen partial pressure of 0.2 approximately. It is 0.209 something, but we can take it as 0.2 for all our purposes. So this is for the atmospheric air, but at a given temperature for a metal, just the temperature and the material itself will not determine whether we can oxidize. We need a sufficient oxygen partial pressure, sufficient oxygen activity to form an oxide layer, oxide over metal surface. So if you want an equilibrium between metal and the metal oxide, there is an equilibrium partial pressure that needs to exist, or else we cannot have oxide formation. So let's take example of iron here. That is the example given already, demonstrated already in this case. Let's draw a line to mark what I'm talking about. So this is the iron to iron oxide Fe2O3 line. So, and then let me talk about the temperature, that is (800°C). Actually, it should have been 800, but it's not intersecting. It is the temperature line. Probably I will use a different color for the temperature line here. So there is a temperature line So let's say the intersection point here is called as N, and then what we do is we have this point O on the leftmost corner of the plot. Then what we do is we draw a straight line to intersect this point N, which is formed by intersecting the iron oxide equilibrium line in the free energy versus temperature plot and our constant temperature line, this is the blue line. So if we draw a straight line to intersect that point and continue drawing this line, this is the dotted line in the actual diagram. So if you draw this line, it is intersecting the outermost line somewhere at 10 power minus 15. So at this 800 degrees Celsius, if I keep a piece of iron in an atmosphere that contains oxygen partial pressure greater than 10 power minus 15, then I can have oxidation. So I may ask a question, if we keep iron in open atmosphere and heat it to 800 degrees Celsius, will oxide form or not? The answer is yes, because the atmospheric oxygen partial pressure is 0.2. So you keep a piece of iron in a furnace with air flowing around it. So at the surface, the oxygen partial pressure is 0.2, which is much higher than the 10 power minus 15 value, that is the dissociation pressure. If you had 10 power minus 16 oxygen, then you would not form oxide at all. Oxide cannot form if you have oxygen partial pressure less than 10 power minus 15 in this case. So that is how this is relevant, and then we will discuss this in further detail when we discuss the parabolic growth kinetics of oxide. But this is very important, and the reason the parabolic growth kinetics is experimentally relevant, because we can predict how much oxidation will take place over time, and that is important for industries to predict the service life of the component. If over 1000 hours, if I use, I can do experiments for 1000 hours, but industrial service times are much greater than 1000 hours. So I cannot keep doing experiment to 100,000 hours. So that is not possible. So what I will need to do is, if I understand the kinetics and if I know the growth law, then I can use that to predict that whether the oxide scale will grow to a particular thickness, whether my structure can structurally remain intact for the given service time. So that is the question that we can answer. So for that we will use parabolic kinetics. The parabolic kinetics understanding will require you to understand the effect of partial pressure on the equilibrium between oxide and metal. So that's why I'm spending more time on explaining why this is happening, and these are important even for a practical application. These are not just dry theory, even though it would look like dry theory here. So let's move on to the other axis and how they are relevant for predicting oxidation or oxide formation. So the next axis that we are going to look at is the hydrogen water vapor ratio. So this is a very important reaction in the context of hydrogen powered turbine technology, where we want to use hydrogen produced by several sources. Like this hydrogen burns, so we combust hydrogen, we burn hydrogen, and this is half O2, and what is our byproduct? It's just water. So if we can just burn hydrogen and use that energy to heat up steam and turn the turbine, then in this process, this particular process, the combustion process itself does not emit any kind of carbon dioxide. So the carbon footprint will go really down if we use these hydrogen based turbines, where we use hydrogen as the fuel. So in this reaction, if you know the equilibrium constant, that we have tables, we can determine the equilibrium constants of this reaction. So if we know the reaction at a particular, as a function of temperature, what this is the equilibrium, K equilibrium. If you remember concepts from chemical thermodynamics, it is nothing but the product of the combustion, that is H2O, that is oxygen. This is a water vapor partial pressure, because it's a gaseous form. We are going to produce steam. It is not just water molecule. It's a partial pressure of H2O divided by partial pressure of H2 times root of PO2. So indirectly, this is also representing this. I am taking H2 by H2O ratio by convention, but if I want to equivalently represent a partial pressure, then I can convert that. This is equal to PH2O by H2. So we need to consider PH2O by H2, and then in the denominator we have the equilibrium constant K. So this is inverse of this number that can represent equivalent oxygen activity in the environment where this reaction is taking place. So I have also posted some links from companies like GE for you to understand this technology, and we can produce this hydrogen in several ways and store it in different ways and use it as fuel. So if you are interested in how hydrogen based land turbines are operating, you are free to refer to those links. But this is why we are concerned about this line. Now when you are talking about using this ratio, you need to draw a line from this point, the point H. So what does it mean that if I draw a line from here, if you are talking about an oxide, for example copper, at let's say 700 degrees Celsius itself, let's take an example of copper at 600. So how can I determine the hydrogen water vapor ratio required for the Cu2O formation? Then what I do is I cannot can I intersect this line? Yeah, very slightly I can intersect this line. If I intersect that line here, so let's erase this particular line here. So except when we have very low hydrogen to water ratio or very high water to hydrogen ratio, we cannot form oxide for copper. If you use this green curve, same logic, but you need to draw a line from the point H on the left side of the axis. So that is with the water vapor. We were discussing about the hydrogen water vapor ratio with the example of copper. Now let's move to the third line, which is the CO-CO2 ratio line. So why is this relevant? This is relevant due to an example where we use carbon dioxide. There is something called a carbon dioxide, supercritical carbon dioxide power generation technology. I have also given you a link to a write-up that talks about the supercritical CO2 reactors, and I have also attached a review paper on this topic, how it is coming up. It's a new technology that is coming up, another clean energy technology. So in this reaction, what happens in this process, the oxidation takes place because the carbon dioxide dissociates into carbon monoxide plus oxygen, an atomic oxygen. This absorbs on the metal surface and it can oxidize. So this reaction but to consider this, we also need to think about this reaction. So if we want to convert that into oxygen partial pressure, we need to remember that two oxygen can recombine to form oxygen molecule. So then the equilibrium constant for this reaction becomes PO2 times AO square. We need to consider because this is atomic activity. Atomic oxygen activity. So if we know the atomic oxygen activity, which can be approximated because this is absorbed oxygen, that can be approximated by the surface coverage. Then if you know the equilibrium constant for this reaction, so we have the relation activity of O square, O is equal to root of K, let's say it is K1 by PO2, because for this reaction the K value is equal to PCO times activity of atomic oxygen by PCO2. That is because CO2 and CO are in gaseous state, but oxygen is absorbing on the surface as atom. It's atomic oxygen. So using this relation, the inverse of this ratio, PCO by PCO2, that's the line here, the inverse of this. So we can consider PO2 is actually equivalently represented by not inverse of this, it is just the ratio, this ratio itself, the CO2 ratio, because we can derive these reactions a bit. PO2 is equal to, let's replace AO by P root of K1. So K1, we can erase this AO and replace that with K by, this is K, let's say this is K2, okay, this is K1 by PO2, so it is K2. So using this thing here, instead of AO we put that, what we have is PCO by PCO2, that is the fraction that is there in the oxide, the axis represents this value, and then you have this root of K1 divided by PO2, the oxygen partial pressure, that's equal to K. So if you want oxygen partial pressure, K2, this is K2, this is PCO actually, PCO by PCO2 times root of K1 by PO2, and then PO2 can be written as this square, let's use series things. You don't need a root here, so now we can draw this ratio square times by K2 square. Then we need to erase this guy and write it as PO2. So equivalently we can write this as, so the K1 and K2 are equilibrium. K1 is for this oxygen recombination reaction, and K2 is for this carbon dioxide dissociation reaction. So if you know the K1, K2 values at a given temperature, and then if you know the carbon monoxide to carbon dioxide partial pressure ratio, take square, so you can then calculate the equivalent oxygen partial pressure for the oxidation process. Same logic as before. We need to now draw a line from the point C on the leftmost corner, intersect the intersection between the metal oxide equilibrium line and the constant temperature line. So let's take an example of silicon. So let's take again 600 something, draw a straight line here, then this is the intersection point approximately, then draw a line, and intersect it at the innermost auxiliary axis here. So then for this silicon to oxidize to silicon oxide, we need very high carbon monoxide carbon dioxide ratio, which means that this reaction is rather in a very advanced stage. So lot of carbon dioxide molecules must dissociate to carbon monoxide and oxygen for silicon to oxidize at 600 degrees Celsius under this condition. Under 600 degrees Celsius, if you keep a silicon wafer or something at 600 degrees Celsius, and if you do not have this carbon dioxide, you just purge carbon dioxide into the environment, and if the dissociation of carbon dioxide into carbon monoxide and carbon dioxide, oxygen, atomic oxygen does not take place, then we will not have oxidation of silicon. So this line and this reaction is also quite important in the steel making process, but we are not discussing in that context, but we are discussing in the context of the supercritical carbon dioxide reactors, where carbon dioxide can oxidize the metal alloy component that is used in the power generation apparatus. One of the main drawback of this Ellingham diagram, because it represents equilibrium between metal and metal oxide, and this considers oxide formation free energy just from a pure metal standpoint. So this is the reaction between aluminum. If you have a piece of aluminum and oxygen, and it reacts with oxygen to form aluminum oxide, so that is what it considers. Yeah, it is very relevant and it can be used to give us a sense, but is it a same in a commercial alloy which will have multiple elements in the alloy, and the elemental oxidation need not behave exactly same as it would behave in, let's say, for pure aluminum, or pure aluminum should not be even there in solid state beyond 660 degrees Celsius. But aluminum, which is there in a nickel-based superalloy, it can still stand until the melting point of the alloy itself. So we need to understand, so the aluminum oxidation and the oxidation of aluminum which is present in the alloy will be definitely different from the pure aluminum that is oxidizing. So we need to use some more additional thermodynamic stability diagrams to describe what is the oxygen pressure, the dissociation pressure of different oxides in an alloy. So that can form over an alloy surface. So if an alloy oxidizes, it will result in formation of multiple oxides. So we have a concept called as the emergence condition diagram. So this is a plot between the phase fraction, the weight percentage. In weight percentage, there is a phase fraction here. So weight by weight. So this is a number that's not a highly relevant number here. This would just say how much of the pure metal that was present, the single phase solid solution of an alloy will convert into oxide. So, and we have the partial pressure of oxygen in the x-axis, and this is for a nickel-based superalloy, which we will discuss later in the lecture. The MAR M247 alloy, which is a alloy that is used in the turbine center frame. We will discuss in the case study I am going to show you. We will again see this diagram, but this is an alloy that consists of nickel, chromium, cobalt, aluminum, tungsten, and tantalum. So I'll show you the exact alloy composition later. So it's a very complex alloy with too many alloying elements. So as I said, in atmospheric air we will have 0.2 oxygen partial pressure, which means we are at this line. So that is the oxygen partial pressure. If we keep a piece of this MAR 247 in the air, at the surface, that's at the pristine surface, we have oxygen partial pressure of 0.2. Then we will form these oxides. So predominantly we will form nickel oxide, and we will also have this penal oxide, this nickel aluminum or a nickel chromium oxide, and we can also form this nickel tungsten oxide and also the aluminum tantalum oxide or the aluminum tantalate. So the mixture of these oxides can form thermodynamically. Whether they will form or not, it's also going to be dependent on kinetics, because here we have this tungsten and tantalum, which are extremely slow diffusers. So that has to be seen later, but just talking from pure thermodynamics. That is also a disadvantage of Ellingham diagram, but emergence condition diagram also has this advantage, because it also cannot consider kinetics, because there is also a thermodynamic diagram. So the oxide that forms on the surface immediately, if you expose a pristine alloy surface to 0.2 oxygen partial pressure, you will form these oxides. So we can predict what kind of oxides will form. This is at I forgot to mention, this is at 1100 degrees Celsius. And we can also see, in terms of, if we look at this diagram at other way, that aluminum which is present in the alloy can oxidize to form aluminum oxide when I have an oxygen partial pressure of 10 power minus 25 to around 10 power minus 20. So up to this I can form kind of aluminum oxide, and then there is chromia here. You can form chromia here, and we also can form, in this range we can also form this chromium tantalate. So below 10 power minus 25 we cannot form alumina at all. Alumina will not oxidize at all. That's the theory. But if you look at the okay, let's say I know pure aluminum is not going to be in solid state at temperatures above 660 degrees Celsius, but let's assume if we can extend this solid aluminum into the temperature range where it is relevant. If you want to use Ellingham diagram, you will choose 1100 is somewhere here. So then you draw a line from the oxygen partial pressure line to the point of intersection. So sorry, this was not drawn properly. My pen is not working exactly the way it should. So actually this is not perfect, so we need to do somewhere here. That is the correct line. Ignore this line. Yeah, this is more straight than the other line. So we think this says aluminum will oxidize to aluminum oxide anywhere above 10 power minus 30 oxygen partial pressure. But in this alloy, it is not 10 power minus 30, it's around 10 power minus 25, which is 5 orders of magnitude higher than what you would expect for pure aluminum. So in pure aluminum, if alumina has to form, it needs minimum oxygen partial pressure of 10 power minus 30. But for this alloy, we can form oxygen oxide only if the oxygen partial pressure was 10 power minus 25, which is 5 orders greater than. So this is to demonstrate that whatever we see here is in the Ellingham diagram is not applicable in real alloys. So we need to be careful. But it gives some sense that okay, aluminum forms more stable oxide than silica or chromia. That's what we get. That is the very useful information that we get from the Ellingham diagram. So Ellingham diagram can give us a direction, but if we want to look at commercial alloys that are industrially relevant, we need to go for these advanced diagrams. So because we need to consider phase stability from a holistic standpoint for an alloy, which is very different, which can be very different. As I showed you, there is a 5 orders of magnitude difference between pure aluminum oxidation and the alloy oxidation. So we need to bear this in mind, and we need to use appropriate diagrams, because at the time Willingham developed these diagrams, this was the best he could. Now we have capabilities to generate these kinds of advanced phase stability diagrams which we can make use of. So if there is a possibility to use this diagram, we can use it. Simple.
So far we have been talking only about environments that contained only oxygen, or even in environments containing multiple gases, we were just interested in the oxygen activity using oxygen partial pressure and how oxidation takes place in different environments. That was discussed in the, when we were discussing these auxiliary axis, we were telling how oxygen activity in different processing atmospheres, such as atmosphere containing water vapor and hydrogen, or carbon monoxide and carbon dioxide. But in addition to oxidation, we can also form things such as carbides, especially when we were talking about this CO2 equilibrium. We missed one thing. We can also have carbon activity, equivalent carbon activity. So if we consider carbon activity, so how does carbon activity come into the picture? Because in that slide, if you can go back, I would have written that, okay, CO2 was splitting into a molecule of COO plus O, this adsorbed oxygen. And then we were only talking about the oxygen activity through this, considering this 2O to O2 equilibrium, this reaction, and combining it and writing in the form to find equivalent oxygen partial pressure based on the ratio of partial pressure ratio between carbon monoxide and carbon dioxide. But there is also another reaction that is possible. This 2CO, they can recombine to form this. Can also happen. So you can derive using same principles of chemical equilibrium, using the equilibrium constant K for this reaction, let's say K3. We can find out the activity of carbon. So that is what is there in this axis, this is activity of carbon, and we can determine the activity of oxygen, that is the partial pressure of oxygen. And then for each of these conditions, for a given alloy which might contain all these elements which are oxide formers, so this is for a different oxide formers such as zirconia. So above this line we have zirconium oxide that is stable, but below this line zirconium carbide is stable. This is one example that is given. This particular example for this figure is this 900 degrees Celsius, and there is some industrial process called as cold gasification. So this is not related to this reactions I am talking about. So this reaction is one such reaction where we can obtain carbon activity. This is in the context of supercritical CO2 reactor, but in conventional fossil fuel based power generation, we have something called as the cold gasification process. It used to produce natural gas, or sometimes what is called as syngas, and now they are also using this as a hydrogen production method, and also to produce carbon dioxide for the supercritical boiler reactor. So here this reaction is usually this is coal, the carbon is from coal, then you produce H2. So here you can produce hydrogen as well as carbon dioxide. This carbon dioxide is then goes into the supercritical carbon dioxide reactor, and this hydrogen
can be used for it can be stored and transported, and then you can use this hydrogen for hydrogen turbine based power generation or something. So this cold gasification is usually considered a really bad process, but if you can use steam and pass hot steam through carbon, a bed of coal, then you can get this carbon dioxide and hydrogen, and that can be used for our clean energy purposes. So in this atmosphere, the cold gasification atmosphere, that is somewhere in the range of 10 power minus 20 oxygen partial pressure and around very high carbon activity in this end, because the coal is, there's a huge amount of coal, pile of coal, and you pass water vapor through this. So in this condition, if you take niobium, that may be present as an alloying element in the alloy, this is in the stability region of niobium carbide. So niobium carbides will start to form. But if you take chromium, we are in the chromium oxide stability region. So we will form Cr2O3 and niobium carbide and tungsten carbide. All others, we will be, the titanium will also be predominantly as oxide. So predominantly is a wrong word. The equilibrium phase is titanium oxide, not titanium carbide. But by convention, this is called as a predominance diagram, where we can find out regions of oxygen partial pressure and carbon activity combination. So this is, you can take this like a map, which gives you an idea whether you are carburizing or oxidizing in the given industrial atmosphere. So there are predominance diagrams for sulfide containing environment. You can have sulfur dioxide, and we can have chlorine containing environment, Cl2 induced corrosion. So in hot corrosion, we also need to consider environments that consist of multiple gases that are very industrially relevant. So in that case, you need to use predominance diagram. So from an exam point of view, you might be asked what is a predominance diagram, and you should be able to explain with examples whatever has been taught in the lecture. But this is very industrially relevant, and we need to be very aware that Ellingham diagram has a lot of limitations. One of the main limitations is thermodynamics. It is just thermodynamics, because even this predominance diagram is purely thermodynamic. So that limitation is still common. So because so far in this lecture we have never considered the kinetics aspect. So that is there for all the diagrams that I showed you so far, but Ellingham diagram is the simplest one, and we can have emergence condition diagrams for alloys, and for multiple gas containing environments we can have predominance diagrams. So this you need to bear in mind, and these are often used in the industry to determine what kind of process will happen, whether intercarburization is happened, because sometimes carburization is done on purpose, but most of the times we do not want these blocky carbides that can deteriorate the mechanical properties significantly. So if the structural integrity of a structural material is compromised, then there is no use in designing alloys that can withstand creep and something. So this is where the reactive environment is playing a very important role in high temperature properties of alloys. So this need to be borne in mind every time when we work in these high temperature chemical processing or power generation technologies in the industry. So far in this lecture we have been talking mainly about the thermodynamics of oxide formation, but when you consider any physical phenomena, it is governed by two fundamental aspects, which is thermodynamics and the kinetics. So we need to, when we study kinetics, there are two things we need to consider in the case of oxide scale formation. One is oxide nucleation, and the second is oxide growth. So we had mentioned about the emergence condition diagram, where we were able to see at a given oxygen partial pressure what oxides have a driving force for forming on the surface. So what that driving force imply is that if you see the metal phase or the alloy phase, and the oxide phase has the lower energy, which means there is a energy difference. If you see these two lines that I am drawing here, this is the driving force between for oxide formation. This is the chemical energy driving force. This is volumetric expressed in terms of volumetric free energy difference between metal and oxide. But for that to happen, so I might have same driving force if I have a different oxide with the same amount of driving force. Let's say we have a so what is the difference between the green curve and the red curve in terms of the driving force? They do not have any difference in terms of the driving force, but if you see the activation barrier, you need to go through this transition state. This is the activation barrier. This activation barrier for forming this red oxide is lower than for the green oxide. So, which means the nucleus of the oxide that might form on the surface initially is more likely to be the red oxide rather than green oxide, even though the both red and green oxide have same driving force for formation. So that we need to keep every time in mind. So nucleation has an activation barrier, so that must be kept in mind. So once a nucleation has happened, so once you have formed nuclei, so how does that happen? This is the metal surface and you have formed nucleus of red oxide and green oxides. So you can form multiple oxides in the early stage, but what grows is the one which has the maximum growth rate. So how does the growth take place? First, predominantly by surface diffusion. You can have a lateral growth of this nucleus, and if the, let's say, if the red oxide has the fastest growing rate, after some time what will happen is that we will enter a situation where this has grown a lot. So you have the red oxide that has grown something like this. So it is fully covered. So there is a lateral growth and coalescence, and it covers, and you form a continuous scale of red oxide with slowly growing internal. It is not internal. It is engulfed within the red oxide which has formed. So I think this kind of example is taken with an example of nickel copper, where thermodynamically you can form both Cu2O and NiO on this nickel copper alloy surface, but because nickel oxide grows faster than the Cu2O, then you generally get NiO scale with discrete islands of Cu2O which is embedded within this oxide scale. So that will happen. So, and once this full scale is formed, then the outward growth of this oxide, which is in this direction, will take place through either through diffusion of metal cations through the oxide scale, and it interacts with the oxygen on the oxide gas interface, or this O becomes this O2 anion, this anionic diffusion that takes place, and you go inside and the metal and reacts at the alloy oxide interface, this interface. So in this case the reaction is taking place in the oxide gas interface, but in this case it is taking place in the alloy oxide interface. Sometimes the reaction might take place within the scale because the growth is governed both by metal cation diffusion and oxygen anion diffusion. So you can describe diffusion by Fick's law, and where this D is the diffusivity of the defect, which is in this case metal cation or oxygen anion. So that's all with the basics. If there is a one predominant oxide that is growing, but in real life conditions we always have multi-layered oxide. So how do these multi-layered oxide form? So that understanding needs to be provided, so which will be shown in the next slide. So I'm going to go back to the example of this emergence condition diagram that was already shown to you. So let's assume a condition where you have this mar2 force of an alloy at 1100 degrees Celsius. This is the alloy surface that you have. So our initial stage at the, let's say this is interface, this is gas phase, like this is gas phase, there is synthetic air, so which is air, and this is alloy. Let's say this is the alloy. The gas is flowing around it. So let's erase this. Once you have seen, you need to understand that this is the alloy and there is a gas. And our initial condition, as I told you, the oxygen partial pressure in an ambient air is 0.2. So which means you go here, so this is somewhere where we are. Here we see we can form spinel, nickel oxide, and the nickel tungsten oxide, as well as this aluminum tantalum oxide. But apparently the red oxide, even though the driving force for this is lower than the nickel oxide at this case, because the fraction can tell us the driving force for formation. So if there is zero fraction, then there is no driving force. If you have a maximum fraction of this particular oxide, then you have the maximum driving force for it. Because this is purely thermodynamic and only chemical thermodynamics is being accounted, though, because free energy has three components. One is the chemical free energy, which is just due to the phase transformation, and there are two other free energies that are important in considering different phase transformations, that is interfacial free energy and the strain energy. That is not considered within this diagram, but let's for a moment let's assume that we care only about the chemical free energy. In terms of chemical free energy, nickel oxide should have been the most favorable oxide, but in this alloy what has been experimentally observed is that the initial oxide is predominantly nickel chromium oxide, which means it's a spinel oxide, so that is the layer that forms. So once that layer forms, let's say this is we'll use a different color for the oxide. I think it might confuse if you okay. So let's say this forms purple color oxide. Even though multiple oxides are favorable, you might have some embedded oxide particles inside this thing here, but predominantly this. So let's say this is the oxide that we are talking about. Sorry. So let's say this is the oxide scale that has formed, which is the nickel chromium spinel oxide. And then what happens is that once this has formed, so we'll talk about two interfaces here. One is the oxide gas interface. The other is the, let's say, the alloy oxide interface. Alloy oxide interface. Another information that we get is that at the interface between the alloy and oxide, the partial pressure is somewhere 10 power. It goes down because there was very high oxygen activity on the surface, a pristine alloy surface. Once this scale has formed at this interface, this green color marked interface, the oxygen partial pressure at O2 at alloy oxide interface, alloy oxide. Is much less than 0.2, which is there at the oxide gas interface, and it's somewhere close in getting closer to 10 power minus 15, because there is very little oxygen there at the oxide alloy interface. It's mostly you have because we have a constant flow of oxygen, the partial pressure, oxygen partial pressure at this interface is still 0.2, but in this interface it is much lower. So that creates driving force for an oxide to form, that is a chromia to form. So what will happen inside it is that we have, at this interface, I start to nucleate this blue color oxide, which represents this corundum phase, which is chromia. So then this chromia particle grows and laterally grows, and at some point you form an internal scale. This is a second scale. Now the metal is gone, it has also become oxide, and this is a chromia oxide. This is belonging to this oxide. Now this scale has formed. Now we need to consider another interface, that this chromium oxide alloy interface. At this juncture, the need to go like this. So this is the partial pressure that is prevalent in this interface, which is the Cr2O3 alloy interface. The green interface has now become the spinel oxide and chromia interface. So now, because the oxygen partial pressure at this blue color interface has gone much lower, now it starts to form alumina here. So what kind of color? Let's choose a darker blue color. So now there is driving force for alumina nucleation, and you, at some point after some growth, you create an internal scale of Al2O3. So that is how realistic multi-layered scale. So you might have 4 layers of oxide forming based on their stability and how they are forming, because we always need to know the fact that the oxide gas interface, the outermost oxide gas interface has close to ambient pressure, but the innermost oxide interface should have very low oxygen partial pressure. And sometimes internal oxidation can also take place. Sometimes if there is not enough aluminium, so the partial pressure gradient from the surface, which is the initial surface, will be steeper. So up to a point where I am above alumina formation depth, I can even precipitate out discrete alumina particles. That is detrimental. So let's say this is the alloy interface. I am also having some nucleation, but the growth and the aluminum content is not that high, but oxygen still has access to this surface, so which means oxygen atoms, as I mentioned. So the initial first stage in oxidation is that O2 this is an adsorption site on the surface. There are several adsorption sites. If you look at a surface from the top view of an crystallographic plane, you will have crust and troughs. If you consider this ball model, like you might have, there is an arrangement of atom, and the FCC metal can somehow look like the 111 plane might look. If you look from the top view, if you are looking into this slide, this is how the 3 atoms might be arranged in an 111 plane. So there is a site which is in between these three atoms. There is a trough. There is a valley in which this oxygen can adsorb. How it would adsorb? It will adsorb like so. Then there is, it's reductively adsorbs, which means there is a 2 electrons also involved. Actually 4 electrons, because there is a 4 electrons. So this is an electrochemical reaction that is happening on the surface, by which the oxygen dissociates and absorbs reductively on an absorption site, which is denoted by a star mark here, which is the absorption site here. This is the FCC site in an 111 plane. So this is the first step. So once this oxygen absorbs, it also has a chance not to just stay in the surface, it can penetrate the surface and it can still go into the surface. So if that happens, you have, okay, let's say in this alloy 10 power minus 26 is the minimum oxygen partial pressure that is needed. At the alloy gas interface, this is gas and this is alloy, let's say the alloy. At the surface, oxygen partial pressure was 0.2, which is close to the ambient condition, but it steeply falls, and let's say this is the value for the critical value, the dissociation pressure of alumina. So this is distance as you are going into the alloy from the surface. This is the surface and this is the gas phase, and this is where your alloy is, and you are plotting PO2 versus distance. The x-axis is distance here. So this is the critical dissociation pressure. In this case for more alloy it is 10 power minus 25. So there is a gradient, and at some point it goes below it. So because if you are far into the alloy, if you have a big block of alloy far interior, which might be hundreds of micron inside the material, it does not know that there is a surface outside and it is exposed to a gas. It does not know anything. So there is no oxygen at all, which is extremely low oxygen partial pressure is there. But up to this distance, like this distance, you have oxygen partial pressure that is above aluminum oxide formation level, which means that even though I do not have, let's assume a case where we do not have enough aluminum to form an alumina scale on the outside, external scale, what happens is that in this region you start to form some alumina particles as an internal oxide. This internal oxidation is detrimental to the mechanical integrity. So that is also a result of this oxygen partial pressure. By just looking at the emergence condition diagram, and we can use our knowledge of mechanisms of oxide formation, including the nucleation and growth, and then combine it to explain, rationalize or predict what kind of oxides will form. So you might ask, why do I care about what kind of oxide might form on the surface? Because if you form a less protective oxide, so then I will briefly come to the point, how do we determine if an oxide is protective? So if you form a more protective oxide, so for now, let's say more protective oxide grows slowly once it forms. Like it needs to form, it needs to coalesce, and the lateral diffusion should be fast such that it forms a continuous oxide scale. But at the same time, the outward growth rate of this oxide scale should be slow enough that it does not consume a lot of material. So if you're forming a slow growing oxide, then it is good for the material. So we optimize the alloy composition to make sure that we get a slow outward growing oxide, which means it grows slowly and it consumes less amount of your materials and maintains the structural integrity. And if we can predict what kind of oxide layers will form, then I can optimize the conditions to promote or perform some pre-treatment. Because for example, if you do some argon pre-treatment, argon inherently has lower amount of oxygen partial pressure. You might go to a condition where you can promote this chromia directly, which grows slowly, rather than directly put your alloy into service without doing some pre-treatment. So if we can design some pre-treatment for our alloys based on promoting certain kind of oxides to form over over others, so we can preferentially tune what kind of oxide layer we form if we understand the fundamental processes that are going on. So this will be practically relevant when you develop materials and design alloys for practical applications in the industry.